I am here.
Oh, perfect. We're going to do a resume share. Okay, can you see our screen now?
I can.
You see the slide deck? Perfect.
Yeah.
Okay, I'm going to give you an extra 5 minutes on your presentation time. Thanks for your patience, everyone. All right, Shawn, take it away.
All right. Thanks, Shawn. Again, thanks for having me. I'm going to talk a little bit about some of the work we've been doing with central heat pump water heating. This one's going to focus on some of the products and gaps, and then share a couple of project stuff that we've been working on.
Great.
So this slide here is a background. Ecotope is based in Seattle. Our climate, there's about 2 inches of snow on the ground right now today, so it's a little bit different than California. So a typical building in a typical multifamily building in Seattle, we've got quite a bit more space heat up here, is about 40 kBTUs a square foot a year, and a quarter of that is domestic hot water, resolves to about an EUI of 10, and about a third to a half of that is temperature maintenance. So what are we trying to do here in this decarb heat pump water heating agenda? We're trying to reduce the DHW EUI from about 10 to 3, and we want to sort of be strategic about when we're heating that water. Next. Just a little background on what heat pumps. Heat pumps do not create heat; they just move heat, and they use a refrigerant, changing phases between the cycle in order to produce heat when it seems like there's no heat available. But in this case, you can kind of see with the numbers, you can kind of get the idea of how and why a heat pump can make 185 degree or 120 degree water when it's 20 degrees out, and it's because of the phase change. Next. So the big push right now is on GWP of the selected refrigerants. So the GWP, or the global warming potential of the refrigerants. And why this is a problem is because refrigerants leak. They have about 10% of the climate forcing impact of CO2 emissions. And they're one of the top 2 or 3, 4 targets of most states when they're looking at decarb. And right now there's about three leading types of refrigerant. There's CO2, also called R744, that has a GWP of 1. That's up there and at the top, and that's represented by a few products listed there. And the next one is 134A. This is a GWP of 1430, and then R410A. So these are about the only 3 types of heat pump water heaters that are out there right now. Traditional heat pumps use 134A and 410A, and sort of the new era are going to be targeting some of the low GWPs, the R290s, the 744s, and then some of the drop-in replacements. Next. So one really important thing to distinguish in any central hot water or any apartment building, there's really 2 loads in these buildings. There's a hot water load, so this is the actual heating of the water. This usually corresponds or correlates to 2 peak draws. There's one in the morning and one at night, usually. The second load in these buildings, which you cannot forget, is temperature maintenance. This is the recirc loop, or keeping the loops hot. And this is a 24/7 load. It's purely dependent on your insulation and your surface area. And so the game then becomes kind of a design optimization, trying to keep those surface areas to a minimum. We've worked on several projects. We've seen ranges between 50 and 400 watts per apartment. That is the metric that we use to sort of calculate and compare recirculation or distribution designs. Next. One really important distinction in heat pump water heating, there's devices or heat pumps that are set up to heat water in a single pass, and there's devices that'll heat it in a multi-pass. The multi-pass is similar to like a gas boiler indirect tank. A single pass actually has a device that'll throttle the flow so that you can get a really high lift. So incoming water at 50, out at 140. And the nice thing about single pass machines are you can your storage you've got a higher storage efficiency because you don't have cold water entering the bottom of a bunch of tanks, like if you were to set them up in parallel or in multipass. So when you gang a bunch of tanks together, you get a higher storage efficiency. It also works and plays better, Singlepass does, with time of use and also demand response, and I'll explain a little bit of that later. Next. So one of the biggest challenges that we've had in about 10 years in working on central heat pump systems are how to deal with the temperature maintenance load. And the temperature maintenance load is just the recirc. And one thing that's really frustrating when you get into designing these things, and we've seen a lot of problems in some early designs, are that the recirculation temps are too warm, and so what ends up happening is the heat pumps don't have anywhere else to put their heat, and so you have to do some things to solve that problem. But this can lead to COP degradation. It can destroy your stratification, and it makes the load shift really difficult. So when we're talking about demand response, so having a strategy for recirculation is really important. We've got sort of two internal. I'll kind of review those. So the first strategy is up in the upper left, and what we call that this approach is you've got a primary tank that's heated by a heat pump, and then you have what we call a swing tank, and that swing tank is sort of not connected to the primary heat pump, and it's just sitting downstream of your primary flow, and you just flood it every time there's demand in the building. You fill that tank up, and then your recirc sort of slowly bleeds off. We typically put a backup resistance coil in here, but if you size it correctly and we keep the primary at about 150 degrees, we've found we don't trigger that resistance element. We've got a couple pilots going now sort of testing this theory. So that's kind of more of our more recent sort of developments. And then the second one, usually with bigger buildings, we'll do a dedicated heat plant for the recirc. So the recirc comes in, it gets its own heat pump, and the cold water or the primary domestic hot water heating gets its own heat pump and storage sized accordingly. So these are sort of two solutions, both sort of set up around single pass options that we've had success with. Next. Now we'll sort of look at some of the heat pump water heating products. This slide here shows a photo of a recent install. This is a 60-unit apartment, and we were able to do it with 4 stand-ins. That's less than 5 tons for a 60-unit apartment. The stand-ins pretty much run 24/7, all 4 of them. But this is sort of the extreme on minimizing your heat pump capacity and maximizing your storage. There's quite a bit of benefit there. But anyway, next.
When I presented these, I showed this slide deck actually to Vancouver, like all our government folks, on Thursday and Friday. And one of the questions I got was like, well, how long do they last if they're running 80 to 100% of the time? And Albert Rooks was in the audience, and he, because he distributes stand-ins, and he said, oh, actually, they're going to last 10 to 15 years. It's not going to be a problem. Do you have any thoughts on that?
Yeah, that's a great question. And how long do they last? Well, we haven't had them for more than about 4 or 5 years here in the States, so we don't really know that answer. So hopefully Albert does. But we have found that you can get away with running these things continuous until you get to freezing temps, and so we don't get a lot of that here. We have them today, so all eyes are on this install. But in Eastern Washington, we actually turned them into a block of ice, and the controls weren't quite set up to deal with it. Now the next Gen 3s are set up, but they will actually have an active defrost, so they'll stop heating and they'll reverse the gas and melt the ice and then continue on. But yeah, that's a good question. I think this one is sized, like I said, on the extreme, and if we're looking at other installations, we probably would back off on running them 24/7, but this was an example of sort of a minimal connected load solution here. So yeah, that's definitely something to keep an eye on.
So you're running essentially 15 apartments on one stand-in in terms of its compressor, right?
Yeah, and then there's about 800 gallons of storage, including the swing tank.
Okay. but these are like almost 16,000 BTUs, and a standard tank is a 4,000 BTU. So in some ways, it's like as if you had a normal integrated tank that was 80 gallons supporting 4 apartments, which is a lot, but
Yeah.
yeah, this seems to be sort of in line with how single family homes work in terms of your capacity to.
Yeah.
Yeah, okay, cool. Thank you.
Yeah. Yeah. Um, yeah, there were reasons why we did that. One was there were existing tanks there, and they had an original electric boiler, so that was sort of set the constraint. But anyway, getting into this, so I'll start just kind of reviewing what's out there. There's in the 410A gear, really the 410A equipment, none of it's really designed specifically for hot water. So we've been using these systems with double wall heat exchangers and making hot water. In our climate, we can make 120 just about year round until we get into the 30s outdoors, and then we're usually limited on temp. Some of the technologies like VRF will actually limit the output to about 108, so they won't even guarantee a 120. But the key here is that the 410A equipment right now is mostly space heating. Colmec does have a new vapor injection technology, and they claimed 140, but yeah, this is a high GWP offering, and so 410A is probably not going to be the end game for heat pumps. But right now, there's a lot of technology and a lot of inverter stuff that's going to resonate with future designs. Next. The next type of refrigerant is a 134A cycle. So these are specifically set up for water heating. They can make up to 160 and 180. These typically will have a double wall heat exchanger. And 134A can handle about 40 to 110 entering air. Unless you've got a really good defrost cycle, then you can take the 40 down into the 20s or teens. We've noticed capacity hits of about 50% at 45-degree entering. So it's pretty significant there. And so we typically put these devices in parking garages, which stay above 50 in the winter months. We've got designs now that are achieving about 2.6 COP in Seattle year-round, including Recirc. Okay, next. This is a R744 or CO2 as a refrigerant. This is a really high pressure cycle. It runs about 1400 PSI. This is the only currently available UL tested product on the market. It's on the smaller side at 1.25 ton, but we have had success gaining these up to 8 into a single loop, and so that's about 100 unit apartment. That's as most as we've done with these. They are single pass devices. They can make water up to 190, and the lab test for Northwest climate is about COP 3.2. In that Elizabeth James project that I showed you, the 4 Sandins, that one is running about 2.8 or so with the swing tank design. But we don't have a full year yet, so we'll see. Next. And some currently unavailable CO2 products out there. Mayacawa, Mitsubishi Heavy Industries, Itomic, and Sandin are all sort of poised and ready to sort of introduce these heat pumps into the U.S. We hope. I've at least been doing my part, pulling on them to get in, and I know others on this call have been doing the same. They're all 50 hertz right now. 380 volts, 3-phase. So you got to do some transforming if you're going to get them. You can get these field UL tested. I'm told it's about $8,000, assuming you pass all the stuff. Else you've got to fix some stuff. But and temperature maintenance is still a big challenge with these systems. But these would be good applications for medium-sized to larger size multifamily buildings, and we have some plans to start using some of these on some projects. Next. So this slide's really important, and I just wanted to show this. These are the lab tests that Ben Larson at Ecotope did for NIA, and this is showing the Sandin spec sheet. And so over on the left it says COP5, and that's, you know, we do see COP5, but only at one point. If you look over to the right, you can kind of see the curve as a function of the entering water temp for two different outside temps. And you know how these single pass CO2 devices work. They're gas coolers, but they basically start out, they're really efficient at really cold entering water, and that's why you want to set up these single pass devices, because as you can see on the right of the COP chart, they start out at 5 and they race down to 1. So when you get to temperature, you're at COP1, and when you're just starting out, you're at 5. So you can see that setting these up with the coldest possible water entering is really the game on efficiency. The chart on the bottom does show you sort of your D rate. The stuff in the middle is sort of simulated EFs, and we can see in Seattle 2.9. So that COP5 that's in the ratings catalog is really around 3, and that correlates with what we're seeing now out in the field, 2.8 to 3 on this stuff. So anyway, it's really important that that we get these things lab tested so we actually know how they perform, so we can get delivered savings. Next. A little background on some of the project work that we've done: low rise, mid rise, high rise. Quite a few bigger jobs in there, so we've got quite a few bigger plants in Seattle area. Next. Here's a unique one that we just wrapped up. It's a wastewater source heat pump. So right now the focus is all air source, but wastewater source is definitely something to keep in mind. We ran a simulation on this, and the COP came out to right around just under 4 seasonal. So there's potential. I mean, we haven't seen the results out of this, but this is the project, and this is just kind of wrapped up commissioning on this. So it's pretty interesting. So we'll have some more to report on this next year.
Well, related to this, Shawn,
Yep.
some questions going back and forth is: does drain water heat recovery work well with heat pumps?
Yeah, like the power pipe or the DFX stuff. Yeah. We used to do a lot of the drain water heat recovery, and we would see, somewhere around 75, 80 entering water. And so, if you were to go back and look at what that would do to the COP on that previous chart that I showed, you can see that there is a little bit of a hit on that. So you'd have to kind of balance that, obviously, with how much you're getting off the drain water, and to see if that COP hit was a function. If dollars are stretched, you'd have to look at it. I just haven't done it. I usually would say, if you're going to invest in the heat pump, then no sense investing in the drain water heat recovery.
So they work,
so
but you're saying they're not cost effective.
They're not. I mean, last I looked at them in our kind of cheaper power region, they were about a 15-year payback. And so, we can do the calcs on that, but I guess I just haven't. I guess my summary is I don't know, because I've never done those two calcs together, but because we haven't really been doing drain water heat recovery that much anymore. So it's an interesting question, probably not too difficult to calc, but it would be interesting to see the impact on the COP as well.
And you might have to give a little technical knowledge. There's a question on
why.
Yeah. It's okay. Why does incoming cold water lead to greater efficiency? That I think is lost on some people.
Yeah, that's a good question. And it's easily explained in a pH diagram, which is an enthalpy pressure diagram, but that usually gets over people's heads, so I won't go there. But but in the refrigeration cycle, there's sort of a condensing side and a evaporator side, and the colder the water is, what it ends up doing is it positions you better on the next cycle, because now you're further along the chart, and so you get greater capacity, which leads to less energy use. So it's a gas cooler, and you're trying to cool down this gas as part of the thermodynamic cycle. And the colder that you make that water, as you're cooling it down with city water, transferring the heat out, the sort of the better positioning you give the heat pump on that next cycle is probably the way to explain it without having the chart in front of me. All right, next.
Sorry, I was talking to you. I didn't realize. Next slide.
Oh, okay, yeah. Sorry, I'd be happy to follow up if you wanted to, if there were more specific questions.
Well, just check out those
to answer.
chats. When you're done with your presentation, if you could put some comments in the chats, that'd be helpful.
Okay. Here's a little project we have going on in LA area, Culver City, and this is a 100-unit senior housing project. We're working on the MEP design for it, and in this specific sort of pilot, we're gonna demonstrate a demand response CO2 central PHW system. So we'll set it up to do all the heating between 8 and 4 p.m. We'll also install a high performance distribution system, and so the goal is to get the EUI of the DHW heating to 3 kBtu square foot a year. Preliminary sizing has shown about a 20-ton single pass CO2 with some fancy controls, and 2,000-gallon primary storage and a 1,000-gallon swing tank. So that's a project. This will be 2021 installed, or at least that's the intended schedule. So we'll see how that goes. Next, and this was responding to Shawn Armstrong asking about some product performance specifications for, say, an idealized heat pump product for multifamily, central hot water. So this would be a low GWP refrigerant. We've kind of tossed around this idea about single digits. So get the GWP to 9 or lower, single digits. Single pass design to enable the stratification, and it improves efficiency on your heat pumps. The product should be capable to make 150-degree water. Even hotter would be better. We've done some calcs at 190, and that does save quite a bit of storage, but you take a hit on COP making the hotter water. It should be operational from -13 to 110 outside. Min COP should be around 3.5 at 47. 5 to 10 ton size. Power requirements. Typically in multifamily buildings, we're either 208 3-phase or 240 single, but 208 3 is most common. Everything's potable rated. Fully packaged controls. Right now, we're setting up all of our heat pump systems with custom DDC controls with alarms and automatic backup systems. This is really the only way to stay sane when we've got issues. I mean, we're still early life on some of this heat pump products, and things happen, and so we have to stay on top of them. But back to the product, fully optimized defrost controls. We use digital thermostatic mixing stations for all of our hot water loops, plants. And having integrated M&V and diagnostics, alerts, alarms is really nice. Colmax just updated their product line, so they've got a lot of controls kind of built in, so that's sort of exciting. And then having some sort of sizing support from manufacturers and the reps would kind of seal the deal as well. So these are kind of what we see as kind of the fitting a lot of the sort of the future problems or ideals. for central heat pump water heating. And I think that is the end.
Woo! Thank you, Shawn.